Z-scores, also known as standardized scores, tell us how many standard deviations an observation is from the mean and in what direction. Positive Z-scores mean that the observation is larger than the mean, while negative Z-scores mean it is smaller. The formula is shown. An observation's percentile is the percent of the distribution that is below the value of the observation. For example, an observation at the 45th percentile means that 45% of the observations can be found below that value. Cumulative relative frequency graphs, also known as ogives, allow you to see the percent of observations that lie below a particular value. To make this graph, we start by looking at a frequency table. This graph allows us to see the accumulating percent of observations as we move rightward through the classes.
A density curve shows the distribution of all the probabilities. It is always on or above the horizontal axis, and the overall area under the curve is always 1. In a density curve, the mean is the balance point of the curve, and the median splits the curve so that the two halves are equal areas. In a symmetric curve, the median is equal to the mean. However, in a left-skewed curve, as shown here, the median is higher than the mean because the lower outlier values pull the mean down. A similar thing happens in the right-skewed curve. When you're adding subtracting a constant a, the measure of location changes, so the center, such as the mean and the median, and the quartiles and percentages will increase or decrease by that constant. Spread does not change, neither does shape, since transformation is applied to all of the data points. When you're multiplying or dividing by a certain constant, the center, quartiles, percentages, and spread will all change by that constant, but the shape does not.
One important class of density curves are normal curves, which describe normal distribution. All normal curves have the same overall shape. They're symmetric, single-peaked, and bell-shaped. Any specific normal curve is described by its mean and standard deviation, both of which are labeled on the normal curve drawing. The mean is located at the center and is the same as the median. Standard deviation also marks the point of inflection on the curve and controls the spread of the normal distribution. Curves with larger standard deviations are more spread out. All normal distributions follow the 68-95-99.7 rule, which states that 68% of observations fall within 1 standard deviation of the mean, 95% of observations fall within 2 standard deviations of the mean, and 99.7% of observations fall within 3 standard deviations of the mean. All normal distributions are the same when standardized, so we can use one table to find the areas under a standard normal curve. The standard normal table, also known as Table A, gives the areas to the left of a z-score under a standard normal curve. For example, question 1, it reads, in the US, the average IQ is 100, with a standard deviation of 15. What percent of the population would you expect to have an IQ below 85? It is important to note that this question is asking for the area left of the z-score that we will calculate. We calculate the z-score and using the z-table, locate negative 1.0 on the z-score row and, in the remaining digits column, 0.00. The intersection gives 0.1587, which is the area to the left of the z-score of negative 1.0. Thus, the answer is around 15.87% of the population has an IQ score lower than 85. Using a calculator, go to second bars, select normal CDF, enter in a really large lower bound, and as an upper bound, enter 85, 100 for the mean, and 15 for the standard deviation.
So working backwards, we can go from areas to z-scores. So for example, what if we're asked to find the 95th percentile of the standard normal curve? So in this case, we're looking for the z-score that has 95% of the area to the left as shown in the figure. So there is a 3-step process to doing this. The first step is going to be to state the distribution and the values of interest. You always want to draw a normal curve with the area of interest shaded and the mean, standard deviation, and the unknown boundary value clearly identified. Then you're going to want to perform calculations and make sure to show your work. So there are 2 ways to do this calculation. One is using your calculator. You're going to go second variable, and then you're going to find inv norm. And in inv norm, you are given a prompt to give the area, the mean, and the standard deviation. So the area in this case is going to be 0.95. The mean is going to be 0, and the standard deviation is going to be 1. So once you've entered all those in, you can input it, and you will get a value of 1.644 or 1.65, and that gives you the z-score for this percentile or this area to the left of z. So you can also use Table A to go from areas to z-scores. So Table A, essentially the entries give you the probability of lying below z. So I want to find the one that corresponds to 0.95. So looking at the table, I find 0.9505, and that lies at a z-score of 1.65. So since that's very similar to what I got in the calculator, I can use this to answer the question. So now looking at the normal probability plot, some software plots the data values on the horizontal axis and the z-scores on the vertical axis, which is preferred. So that's what I have here. And if the points on a normal probability plot lie close to a straight line, then the data are approximately normally distributed. And you want to look for systematic deviations from a straight line, which would indicate a non-normal distribution.
For more practice with calculating and interpreting z-scores, go to the 2011 free response question number 1.